Giuseppe is going to talk about investigation of the hadron nature of high energy photons with PeVatrons.
So, can you hear me?
Yes, we can.
Okay, let me share slides.
Sure, please.
So, can you see my
Yes, we can.
slide?
Yes.
Okay, let me.
Whenever you're ready, please.
Yeah, yeah, sure. Okay. Okay, so unfortunately I was not able to be there with you, so I thank the organizer for the opportunity to do this talk remotely. So the goal of this talk is to introduce the idea that we can study some feature of the hadronic nature of high-energy photons with gamma-ray astronomy, with PeVatron, with high-energy gamma-ray astronomy. So as you know, in the last years, some experiments at high altitude, first of all LASO, but also HAWK, Tibet Array, detected a number of photons above 100 TeV in a nearly background-free regime. This means that for the first time, we have a pure sample of shower produced by high-energy photons. In particular, LASO is observing about 4,000 photons per year above 100 TeV and about 20 photons per year about 1 PeV. This observation offers the possibility to study characteristics of photon-induced showers without Monte Carlo and to compare with Monte Carlo simulation. And in particular, this is, my opinion, the important point, this observation allowed to measure for the first time the pion photoproduction cross-section, even at energies not yet investigated or marginally investigated at accelerators. These studies, as I will show you in this speech, are very important to study characteristics of the photon-hadron interaction, some aspect of QCD. In the near future, new experiments in the southern hemisphere, like SWIGO, but also Alpaca, are expected to detect a larger number of PeVatrons, thus extending these studies at higher energies. So why photon-hadron interaction is very important, and a measurement of the photoproduction cross-section at high energy is very important. So as everybody knows, the photon is the gauge boson of quantum electrodynamics. It's regarded as a point-like structureless particle. But with increasing energy, after the interaction with a Coulomb field, through the pair production process, we know that the photon could materialize, transform in a pair of electrons. Therefore, we can interpret pair production as arising through the scattering of the photon constituents of the photon, the electron and the positron. This illustrates the point that at different energy scales, different aspects of the dynamics of underlying dynamics become visible. In high energy photoproduction, in many aspects, the photon exhibit an internal structure very similar to that of hadron, with a small probability of order of the coupling constant alpha. On general ground, photoproduction is a process where something is produced by interaction of high energy photon with an hadron, something like pions as an example, and muons through the pion decay. This explains why photoproduction is so important in gamma-ray astronomy, because pion photoproduction is the main process to produce muon in gamma-induced showers. And as you know very well, gamma-ray astronomy with the limit in gamma-ray astronomy, the problem in gamma-ray astronomy with shower array is that the signal of photon is completely overwhelmed by a shower produced by charged cosmic rays by the background. For energies greater than 1 TeV, the signal due to the photon is of order 10 to the minus 3 the background cosmic rays. And as you know, it's not possible to veto with some anti-coincidence shield as a satellite experiment, an air shower. In addition, cosmic ray showers are very similar to gamma ray shower. But in 1960, these guys suggested that we can identify and reject the showers due to cosmic rays, looking for abnormally small number of muons in showers. And this is the so-called the muon-pure technique. The muon-pure technique, the reason why the shower induced by photons are muon-pure is due to the ratio between photoproduction and nucleus-nucleus cross-section. This ratio of the order 10 to the minus 3, therefore we expect that the muon content in gamma-induced shower is of order 10 to the minus 2. The main limitation of this technique is due to the fluctuations in hadron initiated induced showers and due to the small number of muons. And as you can see from these plots, the discrimination capability increases with the energy, but also with the area of the muon detector. Therefore, we need to operate very large muon detector. And the other crucial point is to evaluate, to study the fluctuations, to evaluate to study how frequently hadronic showers fluctuate in such a way to evaluate muon content as the one resulting from gamma-induced events. And as you understand, this strongly depends on the photoproduction cross-section. But as said by Tom Geiser, ironically, early indication in the first experiment exploiting the muon-pure techniques, first indication are that the signal seem to have the same muon content as the background. In fact, many years ago, in this decade, some experiment reported evidence of gamma emission up to the PeV from some sources like Cygnus X-ray, but the striking feature was that the signal coming from Cygnus X-ray, this shower were not muon pure as expected. And in addition, two underground detectors, Sudan and Nusex in Italy, observed, as you can see from this plot, observed an excess of TV muons pointing in the direction of the Cygnus X-ray, suggesting that we can exploit astronomy also with muons. But new experiments, more sensitive, new analysis technique set only upper limit to the flux of ultra-high energy gamma rays from any source. But this was very interesting because the detection of muons from cosmic sources is very difficult to explain according to the standard model of particle physics. Different authors, this is an example of a contribution by Felix Aronian. Different authors suggested the role of new particles, some high energy resonance in the gamma proton cross-section. This is because the search for muon emission from cosmic sources is a search for exotic physics. As I said, this was not confirmed by new experiment, more sensitive, but it's intriguing. The LASO recently confirmed the emission of photons from the Cygnus region up to the PeV range. Therefore, the study of photoproduction process at very high energy, the measurement of photoproduction cross-section above 100 dV, is very interesting, not only for historical reason. This is the muon-pure technique applied by LASO, the best experiment exploiting the muon-pure technique to detect shower with the array of scintillator muon detector at very above 100 TeV, as you can see, and as expected, the number of muons in a gamma-induced shower is very small compared to the number of muons in a proton-induced shower. And operating a very large, unprecedented large muon detector with an area of 40,000 square meters LASO obtained an impressive background rejection capability at level of 10 to the minus 5, which allowed to discover emission from the PeVatrons. So as I mentioned, photons of very high energy behave as an hadron when interacting with other hadrons. This means that the physical photon can be interpreted as a superposition of a bare photon and a small hadronic component which fill the conventional hadronic interaction. In this plot, you can see a compilation of different cross-section, gamma proton cross-section, producing different hadrons, the so-called vector mesons. In this interaction, the cross-section of photons behave very much like hadronic cross-section. And therefore, as I said, the photon appear to contain quark and gluon. The simplest model for describing the hadron nature of photon is the so-called vector meson dominance model. This model was proposed in 1960 by Sakurai to explain, before the introduction of QCD, to explain this puzzling, at the time, puzzling observation. Therefore, the interaction between photon and hadronic target occur by the exchange of an hadron between the addressed photon and the hadronic target. As you can see from this Feynman diagram, the photon transforms in a vector meson, neutral vector meson. According to the quark model, we know that this means that in a large sample of interaction, the photon behaves as a rho in 75% of interaction, as an omega in 8%, and as a phi in 70% of interactions. And in this model, the idea, the Sakurai idea, was to describe the photon-hadron interaction in two steps. First, the photon materializes in the vector meson nearby the interacting hadron, and then this vector meson interacts strongly with the hadron. We have, roughly speaking, we have two kinds of processes. One process with a virtual photon. Through this virtual photon in the diagram A, we have a modification of the target charge distribution, or we have a real photon. This real photon, as you can see in the plot, be transformed in a vector meson before the interaction with hadrons. So in this plot, you can see a compilation of total hadronic cross-section. As you know, the hadronic cross-section is measured with different techniques due to large extent of energies and different target used. As I said, the pion photoproduction is the main process to produce muons in photon-induced extensive air shower. This means that the knowledge of this cross-section is crucial to evaluate the expected number of muons in gamma shower to set correct threshold to discriminate in gamma ray astronomy between the signal and the background. The measurement, the study of this total hadronic cross-section has been then done by Auger up to an energy of about 60 TeV in the center of mass. But information of photoproduction cross-section are limited to about 200 GeV from data collected at Hera. Above this energy, we have only extrapolation. Extrapolation, you can see in this plot, the gamma proton and gamma gamma cross-section are simply obtained by the proton-proton cross-section, multiplying this, the proton-proton cross-section by some factor. This is the core of the so-called factorization model. And in Monte Carlo simulation, up to the highest energy to study cosmic rays, we simply you use these extrapolated cross-sections. As I said, we have different models to extrapolate the photoproduction cross-section. These models can be summarized in, as I said, factorization models or microscopic models. with quark and gluons. The important point, as you can see in this plot, showing different models, extrapolating the photoproduction cross-section above the era data, we observe remarkable differences between different models. And then this means that we expect, we have different muon content according to different model which we put inside Monte Carlo simulation. Again, on the factorization model, this is the widely used model. You can see the photoproduction cross-sections, as I said, is derived from the proton-proton cross-section multiplied by a factor. This factor can be evaluated at very low energy according to the vector meson dominance model. And this is the factor used in the previous plot I showed. This factorization model is based on independence of the energy of the cross-section. And the crucial question is following. Is a photon like a proton just multiplied by a constant factor? We can investigate this hadronic structure of the photon only with gamma ray astronomy above 100 TeV. This is an example discussed in this paper showing that according to these two different models, we have a very different behavior in the energy of muons at Auger energy and so on. This just to say that the photoproduction cross-section, one of the main important processes in astrophysics, have an important effect on expectations. So normal muons in showers are related to the elemental composition and the characteristic of hadronic interaction. This is a well-known plot showing the difference between muons and electron sides for proton and iron. The number of muons increase with energy according to this relation. On the contrary, the photoproduced muons, both in gamma-induced and cosmically induced showers, is nearly proportional. It depends on the number of photons, therefore nearly proportional to the shower size maximum of the shower. And this is the depends. Therefore, the ratio between these two sizes is behaving with the energy, with the primary energy, according to this relation. The bulk of hadronic cascading gamma shower are produced deep in the atmosphere by low energy photoproduction process. Therefore, let me say that the main photoproduction process can be described by observation of photoproduction made at Hera collider. Therefore, we can be confident that the large part of the cross-section, GeV cross-section, is well known. We can evaluate, we can include muons in the simple Heitler toy model. We can include muons in this way. Everybody knows the Heitler toy model. The number of photons is 1/3 of the total number of particles. We have a large number of splittings. In the cosmic ray physics, muons of interest have an energy greater than 1 GeV. Therefore, we expect that after 15 splittings, the energy of muons is reduced to the GeV after in a shower induced by photons of order of PeV. And the number of muons produced by photons is due to this relation, is given by this relation, where n gamma is the number of gamma, and gamma is the ratio between photoproduction and per production cross-section. This ratio is the order 10 to the -3. Therefore, we can do simple exercise to estimate the number of muons. Let me say that for a ray located at high altitude, at example for 1,000 meters above sea level, the maximum number of splittings is about 16, given by the atmospheric depth and the electromagnetic radiation length. So we can evaluate the expected number of muons produced in a shower induced by 100 TeV photons. The number of splittings is 13 to reduce the energy of particles at about 10 GeV, and we know that 60% more or less of the photon energy is transferred to the muons. Therefore, to have GeV muons, we need to have about 13 layers. So the expected number of muons is about 20. We can repeat the same exercise for 1 PeV photons. The important point, interesting point, is this evaluation are consistent with calculation we did with Monte Carlo simulation. This is the number of muons greater than 1 GeV in shower induced by protons and photons in an area 150 times 150 square meter around the shower core, an area similar to oak. The other important point is due by the fluctuation, because fluctuations in number of muons in shower induced by photons much larger than the fluctuation in muon size in proton-induced showers. This is due to the fact that there is the photoproduction is a very rare process that can happen also in the first stage of the shower development. Let me show you what I mean. This is a simulation with Corsica, 1 PeV photons at 20 degrees at very high altitude. You can see this large fluctuation in these two showers. The number of muons is similar, in the same order of magnitude of the number of muons expected in a proton-induced showers. This is because the first, in the early stage of the cascade, the photo-produced muons, therefore developed an hadron shower which is indistinguishable from a normal proton-induced shower. This is the limit of the sensitivity of the muon pure technique. But these events that are typically rejected by CATs, usual CAT in gamma ray astronomy, are very important to extend the measurement of photoproduction cross-section at a very high energy. So according to our simulation, at high altitude, the deep first interaction are the dominant source of muon pure hadron shower, at a lower altitude, fluctuation toward the pi-0 rich shower are the main responsible. But the important point, as I said, is to look for photon showers with a muon content similar to the shower induced by protons, to study the photoproduction process at an energy similar to the energy of the primary proton. And we are studying different technique to select these events that are typically rejected by CATs used in high-energy gamma-ray astronomy. In particular, we are studying the lateral distribution of photoproduced muons that in principle is expected flatter than that of normal muons. Concerning the measurement of cross-section, in this table, you can see the number of events used by different experiments to measure the cross-section. This means that LASO, after 3 years of data, the data taking detected about 10 to 4 photons above 10 TeV. Therefore, we can try a measurement of the photoproduction cross-section to setting up the method and to cross-check also the background selection, because if we use the photon selected with the CAT used in gamma-ray astronomy, we expect to have an agreement with the photoproduction measured, the cross-section measured at accelerator, and this is a very nice way also to check if the selection of gamma shower is correct or not. So let me conclude. For the first time, we have the chance to investigate the hadron nature of photons with in high energy gamma ray astronomy using this sample of this poor sample of shower produced by photons. And the studies are underway to improve the selection of photons to investigate the sensitivity of present and future experiment in the southern hemisphere, which we expect to provide a very large sample of PeVatron than of high energy photons. Thank you very much. That's all.